This is the section 2.10, the law of total probability and Bayes rule. First, let me explain the definition of the partition. For some positive integer k, let the sets b1, b2, bk be such that, yes, there are two conditions. First condition is S equal b1 union b2 union up to bk. What is the meaning of this? This means the sample space is the union of b1 b2 up to bk, right? Union of b sets. And second condition is bi intersection bj. This is empty set for I not equal j. This meaning b1 b sets are disjoint, right? They have no any common elements, right? If these two conditions are satisfied, then the collection of sets b1 b2 bk is said to be a partition of S. A partition of S. Let me explain this using three sets. Then k equal 3. Okay. Then let me go with this condition first. So first condition, then S should be equal b1 union b2 union b3, right? And second one, b1 intersection b2 equal empty, b1 intersection b3 is also empty, b2 intersection b3 is also empty. So under these two conditions, I can draw the Venn diagram for this. So understand here, this is the S. So S equal the union of b1 b2 b3, and also b1 the intersection of these sets are empty. Therefore it should be like this. So this is b1 and this is b2 and this is b3, right? Let me show you again very clearly. This is b1, this color, it is b1. b2 is this green color. b3 is this. So you see b1, b2, b1, b2, b3 is a partition of S. Okay, so that is the meaning of the partition of S. Now let me explain Theorem 2.8. Assume that b1, b2 up to bk is partition of S such that probability of bi greater than 0 for I equal 1 to k. Then for any event A, we can write probability of A equal summation I goes to 1 to k probability of A given bi times probability of bi. This is the theorem. So let me explain this using the above examples. It means for the three sets. Yes, again k equal 3. Then we have b1, b2, b3, three sets. Okay, so we can draw this one. That is the S, and there are three sets satisfying the above two conditions. So I draw this one. So like this. So this is b1 and this one is b2 and this one is b3, right? Now they are talking about a set A. I use the set A this. That is a set A. Now you see set A has common areas with B1, B2 and B3. So let me show you. This is the area, the common area with B1, right? So common area is B1. We can write A intersection B1. Clearly, this one is the intersection with B2. So I write down this part, A intersection B2. The last set, this area. This area is the common area with the B3. So that area is A intersection B3. Now we can write down the set A equal A intersection B1 union B2 union B3. And we can use the distributive law. A union B1 union A union, intersection, right? A intersection B2 union A intersection B3, right? So actually you can write down this using this diagram. You can understand that this whole set A equal A intersection B1, right? The yellow part, and then this one A intersection B2, and the last one A intersection B3. So that is over here. You see that. Now, how do we get the probability of A? Yes, let me write down here probability of A equal probability of A intersection B1 union A intersection B2 union A intersection B3. Now you should remember we discussed this A union B equal probability of A plus probability of B minus probability of A intersection B, right? It is for the two sets. So again we discussed this rule for the three sets. It was probability A union B union C equal probability of A plus probability of B plus probability of C, then minus probability of A intersection B and probability of A intersection C minus probability of B intersection C and plus probability of A intersection B intersection C. So we know this one. So now think about this and compare with our probability of A. Okay, here A, in our case, A intersection B1 and B, in our case, A intersection B2 and C is this one, A intersection B3, right? So A is this one, that way. So apply that. When you apply this rule for our case, you see A intersection B1. It means this A here, right? A intersection B1 union A intersection B2. That is the B. So then here we have A intersection B. That means that in our case A intersection B1, then this intersection A intersection B2, right? So if we know these two, this and this, so this is not the one, but yes, this set and this set of events are disjoint. Therefore, this intersection is also disjoint. That means this is empty, right? So what is the probability of an empty set? It is 0. Therefore, this becomes 0, this becomes 0, and this becomes 0. Therefore, this also, the intersection of each three sets become 0. So then In our case, probability of A equal probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection B3. So probability of A given B1 for the B1 equal probability of A intersection B1 divided by probability of B1, right? So using simple math, you can write probability A intersection B1 equal probability of A given B1 times probability of B1. So use that over here. We can write down probability A and B1. We can write probability A given B1 times probability of B1. Similarly, we can write this A given B2 times probability of B2. The last one, probability of A given B3 times probability of B3. So this can be written for our case I equal 1 to 3 probability A given Bi times probability of Bi. So this is the probability of A. So actually the theorem, I proved the theorem for the 3 sets. But this is not the general case, proof of the general case. For the proof of the general case, please go to the theorem 2.28 in the textbook. Alright, theorem 2.9. So assume that B1, B2, Bk is a partition of S such that probability of Bi greater than 0 for I equal 1 to k. Then we can write probability Bi given A equal probability of A given Bi times probability of Bi divided by summation I goes to 1 to k probability of A given Bi times probability of Bi. This is called the base rule. So this is very clear. So let me explain this. We know probability of Bi given A equal probability of A and Bi divided by probability of A, right? But probability of A and Bi can be written probability of A given Bi times probability of Bi using multiplicative law, right? Probability of A intersection Bi equal this. Actually, you can use anyway if you need, probability of A given Bi equal probability of A intersection Bi divided by probability of Bi. So then use the simple math, so you can write this one. Therefore, we can use this part for the probability instead of probability A intersection Bi. So I write probability A given Bi times probability of Bi. Then divided by probability of A. Yes, you see it is a partition here, right? B1 to Bk is a partition of S. You know what's the meaning of partition. If it is partition, we can write down for the BA by using the above theorem. This one, you see that. So we can replace this part. So this equal summation I goes to 1 to. So this equals summation I goes to 1 to k probability A given Bi times probability of Bi. So that is the base theorem. In my next video, I will explain some exercises.